Hi guys, nice to see you. How are you doing?
Good afternoon.
Hi. Do you have any questions regarding our previous discussion? Center of mass. I guess, yeah, we've stopped at giving the definition in general case for the determination of center of mass, like position vector, radius vector of center of mass. And yeah, hi. And I promise you that this time we will have some example just to make it more clear how to apply this approach in real case when you need to calculate some center of mass. And today we still need to consider, so actually today we should finish this sub-chapter of linear momentum. And in order to do that, we need to finish with the system of many particles. It's like another way to derive the law of conservation of moment when we deal not just with two particles as or bodies as we did at the beginning. Do you hear me now?
Yes.
Oh, okay. Yeah, I don't know what happened. Just my internet access was not working anymore. But I'm back finally. That's good. So let us, until we still have some internet connection, go and start working. Okay. So we finished. Let us change the camera. Okay. So last time we finished with this equation, which defines in general case the position vector of the radius vector of center of mass, which is 1 over total mass of the system integral of this radius vector of some elementary mass product to this elementary mass and integral all over the body, taking into account all these small pieces of mass. So in other way, it can also be represented as 1 over total mass, sum of Ri delta Mi over all pieces of this system. So this is when we are talking about some extended bodies, so which consist not from separate pieces, but from they are continuous and possess some density. Okay, now let us try to consider some of such extended body and calculate the concentration of the position of the center of mass. So for this purpose, we can consider a uniform metal or any material rod. So here will be our axis x, this is 0. Then at position x, we can consider one very small interval of this piece of this rod, which is delta x. And total length of this rod is L. Then we need to figure out where will be coordinate of the center of mass of this uniform rod with the length density lambda. So we can write that the mass of this very small piece of the rod will be dm equal lambda times dx. Okay, so it's clear. We have some linearly distributed density of this rod within one dimension. So because rod has just one dimension. Okay, now in order to calculate the position of the center of mass, Cx, Cm, it will be equal. We apply this equation, but since it's one-dimensional case, we will operate with x, the coordinate, not with radius vector. So it will be 1 over m integral of x dm, and this we will substitute now dm with its expression, which relates dm with dx, will be 1 over m integral x lambda dx, and we will integrate it from 0 to L for all lengths of the rod. Okay, So what do we get? So lambda is a constant, so we can take it out from the integral. Lambda divided by capital M. And here the integral of x dx will be x squared divided by 2 from 0 to L. And this is equal lambda L squared divided by 2m. So this is an expression, but here we have total mass of the system. So we need, in order to get coordinate, we need to substitute its value. So total mass of the system, M capital, is equal to lambda times what? What do we need to use here in order to get total length? Any ideas? So I already answered my question. Total mass. So in order to get total mass, obviously we need to have a product of linear density to total length. Okay. Then we substitute this total mass expression here in this equation, and we get the answer for our question, which is quite expected, but that is good to double check. So we have lambda L squared divided by 2 lambda L. So lambda and lambda we cancel out, this square we cancel out, and we get L divided by 2. For a uniform rod, center of mass is at the middle of the rod. This is here X center of mass. Quite intuitive result. So now let us consider another case when we have a bit more interesting situation. So let us assume that this linear density of the rod is not constant. So it is some function of x, and let's give this function as some parameter alpha times x. So it linearly increases with increase of x. So in this case, our position of the center of mass will not be defined by the so easily at the middle of the rod. So it will be shifted. Let us calculate how much. So we do the same procedure. X center of mass equal 1 over total mass integral of x, and instead of, let's write dm, so to be clear and consistent, then we have 1 over total mass integral of x. Instead of dm, now we put dm is equal to so it's equal to lambda d x, and this lambda is a function of x. Then we put alpha x dx. Okay, so this is alpha x dx. Alpha is a constant. We can take it out from the integral. Integral x squared dx from 0 to L. This is equal to alpha over capital M x cubed divided by 3 from 0 to L. And we get alpha L cubed divided by 3m. Okay, now we need to figure out what is this total M. And here we again need to integrate because we cannot just have a product of lambda to L because lambda is not constant anymore. So total mass is equal to the integral of dm from 0 to L. And this is integral from 0 to L alpha x dx equal to alpha x squared divided by 2 from 0 to L. And this is alpha L squared divided by 2. Okay, now we have this value for total mass and substitute it here for the coordinate of the center of mass. XCM is equal, what do we have? It's alpha L cubed divided by 3 alpha L squared, and also 2 goes to numerator. So this is 2. Okay, alpha we cancel out, cube and square we cancel out, and we get the answer, which will be 2/3 of L. Okay, so we see that in this case, if we come back here, center of mass will be not in the middle of the rod, but it will be shifted somewhere here to larger x because mass is increasing from 0 along axis x. And that's why our center of mass is shifted. So now you have feeling how to apply these equations to determine center of mass of some extended bodies. Okay, now next question we are going to discuss now will be the system of many particles and conservation of momentum in the system of many particles. That is another important way to derive the law of conservation of momentum. Okay, so again, let's recall that position of center of mass for the system of many particles will be 1 over m, sum I equal 1 to n. The n is number of particles, capital N. And here is a product of Ri, the radius vector which describes position of some particle I, and its mass, mi. So this is our starting point. And now let us consider, okay, what will be the velocity of the center of mass? In order to do that, we know that velocity will be equal to first derivative of the radius vector, the position vector. dt. So this is equal to 1 over total mass, sum over all bodies, mi times dri over dt. So we need to take derivatives for positions, radius vectors for each of the bodies and sum it up. And this is equal to 1 over m, sum over I, mi, vi. And this is nothing else as a linear momentum of each body. That's why from here we can write that the product of total mass to the velocity of the center of mass is equal to the sum of all linear momentum of all bodies which are involved in the system, isolated system of many bodies. And this is I, P, I, like sum of all linear momentums, and then it is P total, like total momentum of all bodies of the system. Okay, so with this we agree. Now let us take the second derivative in order to get the acceleration of the center of mass. A center of mass, it is first derivative of the velocity. So dv center of mass divided by t. Okay. Equal 1 over m, sum over all bodies, product of mi dvi dt, and it is equal 1 over m, sum over all I, mi ai. Okay, so now we can write that the product of total mass to the acceleration of the center of mass is equal to the sum of all internal forces, because this is not internal, but all forces which are applied to the bodies. So this is sum Fi. We can write that it's equal to sum of all forces. So this Fi, it is sum of all internal and all external forces, which will define with which acceleration body I, one of these bodies which form the system, will move, and this comes from the second law of motion. Okay, let us rewrite this equation on the next slide and continue. So, product of total mass to acceleration of the center of mass is equal to the sum of all forces which act on the system. Okay, let us then take integral of this equation over some interval of time. So if we integrate MA center of mass, will be over some dt, it will be equal to integral of the sum of all forces dt. So from here, we already remember from our lecture on Monday that the product of force to its to the time along which this force was acting is equal to the impulse of the force. This is the impulse, like total impulse of the all forces which act on all bodies in the system. And this is nothing else as the change in total momentum of the system. So, because when we remember that the impulse of the force equal to change of the momentum of the linear momentum. So we can write the total, the impulse of the force is equal to the change in total linear momentum. Okay, so in isolated system, well, first of all, we need to consider now internal and external forces. Internal forces, according to the third law of motion, we can write that 1F12 is equal to minus F21. So that is why if we have a system of many bodies and they interact with each other, all internal forces are compensated by in pairs. So the sum, we can claim that the sum of all forces which act on the system from 1 to n, they are equal only to the sum of all external forces. Which act on each of the body, because according to the third law of motion, sum of all internal forces, internal, from I equal to 1 to n, between all these bodies in the system will be equal to 0. So taking into account that this sum of all forces is sum of only external forces, we can write, if our system is isolated, definition of isolated system is that external forces are equal to 0 or they are compensated. So in any way, the sum of all external forces which are exerted on the system is equal to 0. So that's why if we consider now this equation, which we rewrote, we can write that m A, center of mass, is equal to the sum of all external forces which are applied to all bodies of the system, and this is equal to 0. So means that product of m, A is derivative of velocity, so dv center of mass divided by t equal to 0. And when derivative of some function is equal to 0, when this function is not depending on the independent variable over which we take derivative. So means that v center of mass, like m v center of mass, is equal to constant, and this is equal to some p total. So this is the conservation of linear momentum of a system of many bodies. So it doesn't matter how many bodies we have in the isolated system, the total momentum, linear momentum of the system, which is defined as product of total mass to the velocity of its center of mass, always remains constant. And also, since the product of this product remain constant, the velocity of the center of mass also by itself a constant value. So means for the system of many bodies, or isolated system of many bodies, the total linear momentum of this system, which is defined as the product of total mass and velocity of its center of mass, remains constant. So this is the definition of conservation law of momentum, linear momentum, in the case of system of many bodies. And just to give you some illustration of this concept, if we consider some projectile which moves with this parabolic trajectory. So imagine it was launched, and at some point it exploded. So since internal forces at explosion are much larger than gravity force, we can consider this system as isolated and assume that we have parts of this projectile moving in different directions because of explosion. However, the center of mass still remains in this point where the projectile was just before the explosion. So if you want to know how will center of mass of these three bodies, like three pieces of the projectile, will move further, so it will remain because of this conservation of linear momentum in the system of many bodies. We have three bodies here. Doesn't matter how they will move with respect to each other. Because of this law of conservation of momentum, the center of mass of these three bodies will continue moving in the same trajectory as this projectile would move without any explosion. So this is one of the very clear illustration of the result of conservation of momentum in system of many bodies. Okay, I think with this part we are done. And we still have some time, that's good, because we need to consider the propulsion motion. That is another important part of this chapter, linear momentum, and we will be done with this. Okay. Let us consider a rocket full with some fuel. So it will be M capital is the mass of the rocket plus some delta M mass of the fuel, and assume that it moves with some velocity v. In some moment, engine starts, I mean, this is not, doesn't matter. I mean, they should be the same. Engine starts, and all fuel in form of hot gases is ejected outside from the rocket. So we have delta M with some velocity we ejected with respect to the rocket. And because of this, the rocket itself with mass M gained some velocity. So we got V plus delta V. Okay, now we want to apply law of conservation of momentum and see what equation we will get. So let us do it. Here will be initial condition, sum of two masses times initial velocity. We don't need vectors here since it's projection on one axis. Then let's consider what we have after this burning the fuel. So we have mass of our rocket times V plus delta V. It gained some velocity and of course momentum. And we also need to add the momentum which was gained by the gases, like the burning products of the fuel. But this velocity is velocity of ejected gases with respect to the rocket. But we operate with velocities with respect to the ground. That's why we need to consider velocity of the gases with respect to the ground. In order to do that, we have delta M, mass of the fuel ejected from the rocket, times V, velocity of the rocket, minus, sorry, not delta, minus V ejected. Okay, so now let us open this parenthesis and see what we get afterwards. Capital MV plus delta MV equal to capital MV plus capital M delta V plus delta MV minus delta MV ejected. Okay, so we look here what we can cancel out. This, this, and that's all. Okay, so eventually we get that the product of capital M, the mass of the rocket, to the change of its velocity is equal to the mass of the ejected fuel times its velocity of ejection with respect to the rocket. Now we need to consider this equation in the limit of delta t approaches 0. So then it will be very short interval of time. In this case, we can write that del dv, change of the rocket velocity, or actually there is another thing what we need to consider. no, let's write first. So it will be capital M times dV equal to delta. It's already not delta, it's dm. It's like very small change in mass because we consider very small interval of time. Dm VE. So in this case, we need to keep in mind that dm is nothing else as minus dm capital. So the mass of ejected fuel from the rocket is equal with minus to the same change of mass of the rocket, because if we eject fuel, it means that we have less material in the rocket, and mass of ejected material is equal to minus of change of mass of the rocket. And change of mass of the rocket is negative because rocket becomes lighter. So if we have negative dm plus, like we have this minus in front of negative, so minus and negative number will give us positive number, which is change of the which is amount of mass which is ejected from the rocket. Okay, so now we do this substitution. We put instead of dm delta m, like dm capital. So it's mdv equal to minus ve dm. Okay, and now we can divide both sides by capital M, and we get a differential equation. Okay, now we need to solve it, and we can integrate two parts, left and right. So assume that initial conditions we have for velocity, we have vi, it's initial, then it goes to v final, final velocity. And the same for mass. We have initial mass of the rocket and final mass of the rocket. Okay, let us rewrite this differential equation on next slide and solve it. Will be dv equal to minus ve dm over m. So in order to solve it, we need to integrate both sides within the intervals which we define. So here is internal velocity, here is final velocity. So here is internal mass, and here is final mass. Okay, so what does it give us? So here is very simple. It will be v final minus v initial, the integral. And this one will be equal to minus ve, because ve is constant, integral of dm over m from mi to m final. So integral of dx over x is equal to natural logarithm of x plus some constant. But this is not, since we have defined integral, we don't have constant. So let us write further. It will be minus ve natural logarithm of m from mi to m final. And this is equal to minus ve natural logarithm of m final minus natural logarithm of m initial. So if we take into account properties of logarithm, the difference of logarithm is the logarithm of the ratio between two components. That will be minus VE, natural logarithm of m final divided by m initial. And another feature of logarithm, if there is minus, so we can get rid of this minus if we flip over this ratio. So it will be VE natural logarithm of m initial divided by m final. And now assume that initial velocity is equal to 0, just for a good example. So here initial velocity is equal to 0. Then we can write that V of the rocket will be equal to V of ejected fuel with respect to the rocket, natural logarithm of mi to m final. So this is the most basic equation which describes propulsion motion. And from here we already see and can make some conclusions. First of all, if we want to increase the velocity of the rocket, which obviously we want to do it, we want to launch it as fast as possible. We want to increase ejected speed of ejection of gases. That's why you need to combine fuel with some oxidizers in that proportions and that choose that materials which will result in the highest temperature of burning. So the gases will be ejected from the rocket from the engine with maximum velocity. And here also it will be proportional, so we need to increase the ratio between initial mass and final mass of the rocket, which means that the mass of the rocket itself, which is final mass without fuel, should be as small as possible. So we want to have this ratio big. So ideally, all rockets should be completely filled with fuel in order to gain the highest velocity. And this is, of course, not possible because you need to have some useful load, which is sent to the orbit. So that's why you need to get a compromise between amount of fuel and useful load. But in any way, nowadays, even with modern technology and engines, it's still about 90% of the weight of the rocket at launch stage is fuel. So only about 10% is useful weight. That's why we have this, and this comes from this equation that it requires to have final weight of the rocket after burning all fuel as small as possible. Also, we can check for the force which is exerted to the rocket by these exhausted gases. So if we come back to this equation, mdv equal to minus ve d m, we can consider the like rearrange it and the force. So we know that the force which is exerted is equal to the change of the external force is equal to the change of momentum. So we have it equal to m times dv over dt. And this can be equal to the absolute value of ejected velocity, dm over dt. And from here, we see that the exerted, like this propulsion force is proportional to VE, so it increases with increase of the speed of ejecting of the fuel, and also to the rate of burning, so-called, because this change of mass over time, it shows how much of fuel we burn per second. And the higher rate of burning, the larger propulsion force will be exerted to the rocket. So that's why at the beginning, when you need larger acceleration of the rocket, when it starts, just when it's launched, you need to burn a lot. So this burning rate should be very high in order to provide enough acceleration at the beginning to the rocket. And later, when you just correct the trajectory, like, or orbit around the Earth, you don't need to burn much of the fuel. So the burning rate can be very small because it's enough to exert small forces to change the orbit. But initially, this should be designed like very powerful engines which burn a lot of fuel and provide large propulsion force to accelerate the rocket. Okay, I think that today we are done with material. It was quite informative discussion. But yeah, I really wanted to finish with this chapter of linear momentum, so you get all information which is relevant for the conservation of linear momentum. Okay, thank you very much for attention. Any questions? If you don't have questions right now, if you look through it and try to digest all this information during weekend, and then if you have any questions, you're welcome to ask on Monday. Thank you very much for attention and have a good evening and good weekend.
Thank you. Goodbye.
Bye.
Thank you. Bye.
Bye-bye.